this is our formula for evaluating surface integrals over vector fields, where we treat the surface S like a parametric surface, and then just take the cross product of the tangent vectors to get a normal vector for your parametric surface, and then you do the dot product between the vector field and the normal vector. It's a double integral because your surface is a two-dimensional object. And of course we integrate over the parameters. So the first thing is that we're going to need to take this surface, which is currently defined as an explicit surface, and then we need to rewrite it as a parametric surface so that we can use this formula. Parametric. Okay. So where these little lowercase r's are, this is just the book's notation, but r is a function of u and v, and that's going to be a way to describe our parametric surface as a vector valued function of two variables. And so we're just going to say that x is equal to my parameter u and y is equal to my parameter v. And then that makes it really easy. We just say that my z coordinate is equal to the square root of a squared minus u squared minus v squared. So not really anything has changed. Nothing really has changed at all. But to use my formula, I need, of course, the little lowercase r partial derivative with respect to u. And so that is going to be a three-dimensional vector. And of course, the first entry is 1, the second entry is 0, and then the third entry, when you look at that square root radical and you take the partial with respect to u, that's going to be negative u divided by the square root of a squared minus u squared minus v squared. Okay. And then when you take the partial with respect to v, of course this vector is going to be 0, 1, and then negative v over the square root of a squared minus u squared minus v squared. Are there any questions so far? Does this part make sense? Okay. Then, obviously I'm trying to do this formula, right? So I need to take the cross product. Let's do the cross product real quick. RU cross RV is going to be the determinant of this thing. No, sorry, I'm thinking about the curl. But this is just the cross product of two vectors, right? So here we go. The entries are 1, 0, negative u over the square root of a squared minus u squared minus v squared. And then 0, 1, negative v over square root a squared minus u squared minus v squared. Of course, the cross product itself is going to be a three-dimensional vector. What's going to be the first entry in my cross product? Yeah, it's not going to be negative because it'll be 0 minus negative u over the square root of all that stuff. So it'll just be positive u over the square root of a squared minus u squared minus v squared. Okay. Then the second entry is going to be what? Negative j times the determinant of that. Yeah. So you're right, positive v over square root of all the junk. Today Gabriel has redeemed himself and he's getting all the minus signs correct.
That's a lot. I'll get it a time.
And then, okay, and then what's the last entry in my cross product? Just one, yeah. Okay, and now I want to use this formula, and I've got the capital F dot product with the cross product, and my capital F vector field is in terms of, x, y, and z, and so just real quick, let me rewrite that in terms of u and v. And so instead of x and y, it'll just be u and v. That's boring. The negative 2z, I can rewrite that as negative 2 times the square root of a squared minus u squared minus v squared. And just as a side comment, remember that u is just x and v is just y, and so at this point we could replace all the u's and v's with x's and y's in the cross product too. We could have done that instead of that, but it doesn't really matter. You get the same answer either way. But again, the integrand of the formula that I want to use is the dot product between f and this cross product, ru cross rx. And so that cross product is going to have u times u over square root all the junk. So that's going to be u squared over all that junk. And then it's going to have plus v times v over all that junk. So I can just add a little v squared up here. That's got the same denominator. And then this third entry times that, I'm going to go ahead and, it's going to look like I'm skipping a step here, but I'm going to go ahead and find a common denominator by multiplying this last entry times the square root of all that junk and then dividing by the square root of all that junk. And so it's going to be minus 2 times a squared minus u squared minus v squared without the square root because I'm dividing by the square root of all that stuff. Okay, so we could collect like terms. And we would get u squared plus 2u squared is 3u squared, and then 3v squared, and then minus 2a squared over square root of a squared minus u squared minus v squared. Or I could just replace the u's with x's and the v's with y's. Because those are the same thing, remember? Okay. But this was just the integrand of my formula. So here I gave you a formula. Now I need to take this integral with respect to u and v, aka with respect to x and y. And so we have to think about what are going to be the bounds and whether we want to integrate with x first or y first and all that. So we're going to integrate over some region, and that region is going to be a region in the xy plane because my variables of integration are dx dy. And the integrand that belongs here that I'm integrating over is actually this whole thing. Okay. But let me pause right here and ask you guys, how would you proceed if you had to solve this double integral? What'd you say? Yeah, I think we should do polar. Because every time I see x and y, they show up as x squared plus y squared. And x squared plus y squared, that's just r squared. So yeah, this is actually going to turn out really nicely if we convert to polar. And I purposefully put off finding bounds of my integrals because the bounds are a lot nicer in polar. Okay. So my new integrand is going to be 3r squared minus 2a squared divided by the square root of a squared minus r squared r dr d theta. And then what is this region that I'm integrating over? What's the region in the xy plane that lies underneath this surface? Yeah, so Stephen is right. The surface itself is the top half of a sphere. So what is the radius of that sphere? A. Yeah, the radius of the sphere is A. Does it make sense what I'm saying here? Like if you look at the surface, square both sides, and then add x squared plus y squared to both sides, and you get x squared plus y squared plus z squared equals a squared. So that's the formula for the sphere of radius A. But this is only allowing positive values for z. It's normally how we think about the square root function if I don't put a minus sign in front. So if we're looking at the top half of the sphere, then the region in the xy plane that lies underneath that is going to be the circle or the disk in the xy plane with radius A. So the bounds of this double integral is going to be describing in coordinates r and theta. We're describing that disk with radius A. And so I'm going to allow my r variable to be anywhere between 0 and A. And then my theta variable is going to be what? 0 to 2 pi. Perfect. Okay. Now at this point, we should notice that there's no thetas in my integrand, right? And so the whole inside integral is a constant with respect to theta. So you can think about taking the inside integral and pulling it out of the outside integral. The integral from 0 to 2 pi with respect to theta is just 2 pi. So that whole outside integral is just going to result in a constant 2 pi. And then what I'm left with on the inside is the integral from 0 to a of, and then I'm going to go ahead and separate this into two different integrals where the minus sign is, so I can rely on that antiderivative additivity. And what I'll get is 3 times r squared over square root a squared minus r squared, r dr d theta, and then minus, don't forget the 2 pi, integral from 0 to a, 2a squared over root of a squared minus r squared, r dr d theta. Oops. And then we'll just solve these one at a time. I'm also going to switch colors so we don't get confused. So this one on the end, this is going to be my orange integral. And for just my orange integral, How would you solve that one?
U sub.
Okay, u sub. U is equal to what?
U squared minus
Yeah. A squared minus r squared. And so then du is
negative
2r dr. Okay, so I've got a negative 2 out front, or I got a 2 in the integrand as well. And I've got an r dr there, so this is all going to simplify nicely to plus 2 pi integral from 0 to a. Well, actually, hold on, what are my new bounds? If I plug in 0,
A squared.
yeah, it becomes a squared. And then up here, my upper bound is 0. Cool. On the inside now, I've got a squared divided by square root of u, which maybe I'll just call that u to the power negative half du d theta. No, there's not a d theta. I forgot that we already did the integral with respect to theta whenever we put the little 2 pi up front. So I don't need to copy that down. Okay. All right, very good. So the a is actually a constant. Yeah. The a is a constant because this is actually just du. Huh?
Should we just make it negative so that it not such?
Yeah, you could do that as well. So you could make that negative and then switch the bounds from 0 to a squared. However you like that. Now the antiderivative of negative half is going to be positive half, and then you divide by half, so it's going to be times 2. So this is going to be something like 4a squared pi u to the 1/2 evaluated at a squared and 0. Let me know if I'm making a mistake, because I feel like there's a lot of arithmetic. And then if I plug in 0, everything's 0. If I plug in a squared, this is going to be negative a. So this is really negative 4a cube pi. Is that correct? Okay. Good. So this whole orange piece of my equation is negative 4a cube times pi. Then we're going to switch to green. And then we're going to go over here. And this will be my green integral. And I'll let you guys tell me how to do this. What's the strategy? What's the calculus 2 strategy that we learned back in chapter 8 for solving this integral?
U sub.
A what?
U sub.
A u sub? So what would be my u?
A squared minus r squared.
A squared minus r squared? Okay. So then du would be equal to negative 2r dr. I could get rid of the r dr. And then this would be a u. What would I be left with up top? I guess I'd be left with a squared minus u, if I did that.
Then we can, yeah.
Interesting. Okay, I didn't even think about this. Okay. I was doing it a harder way. I was doing like a trig sub.
Integration by part.
One trig sub.
That's what I did. It's possible. You just set r equal to a sine theta, and then you draw the picture and everything. But okay. So yeah, let's try this. So we do 2 pi integral 0 to a No, wait. I always forget this. It's so easy to forget. You plug in r equals 0 and you get a squared, and then you plug in r equals a and you get 0 for your bounds. Okay, then this is going to be 3 times a squared minus 3u divided by the square root of u, which is u to the half du. So I'm going to go ahead and break this out into 2 different integrals, where one of them is 3a squared u to the negative half, and then the other one is going to be minus 2 pi integral a squared to 0 of,
Shouldn't it be negative? Instead of the 2, negative, instead of the 2. Like negative 2, negative pi. Negative pi times that. Plus du is negative 2r.
oh yeah, okay. Yeah, okay, so we get rid of the RDR, and then we have a negative 2 that we're eliminating, right? So we have to get rid of a 2 here, like that 2, and then we make it negative. Yeah, okay. So then we flip the sign and get rid of the 2's here. Now it's correct. Okay. So for this, the first one is going to be negative pi 3a squared, and then we pick up another 2, and then we get square root of u at 0 and a squared, plus, and for the second one, we get 3 pi times 2/3 u to the 3/2 power at a squared and 0.
And the screen is frozen.
Huh?
It's frozen. The screen.
Oh, the TV?
Yeah, it is.
Okay. Let's try to fix it. Okay. Cool, so now we plug in the bounds, and 0 is 0, so that doesn't really matter. So we really just have to flip the sign, plug in an a here, and I would get positive 6 a cube pi, right? And then over here, this is going to be negative. The 3 cancels with the 3, and then I get 2 pi times a cube. So this all together is 4a cube pi. And that's the value of the green integral that I started solving over here. And so this whole green part is positive 4a cube pi. So whenever I take the green part and I add it to the orange part, positive 4a cube pi cancels with negative 4a cube pi, and we get 0, right? Okay. And so the answer to this entire problem altogether is just 0. So whenever we take this integral, the surface integral over the vector field, the answer is 0.
So wait, the original way you did it was you did arc sine, right?
Yeah, so the original way I did this with a trig substitution, you said r equals to a sine theta. Then square root of a squared minus r squared would be a cosine theta, and dr would be a cosine theta d theta, and then it works out pretty nicely. Probably about the same amount of work, honestly, but then you'd have to remember your trig subs. I honestly, like, I never remember a lot of stuff about math class, and it's like a hassle whenever I'm teaching because, like, I don't know. If you don't remember something, it doesn't mean you can't solve the problem, right? Like, you can get a little bit scrappy with it. So normally whenever I take an exam in a math class, it's like, crap, I don't remember which trig sub to use, but I can try different things, and I can set, what if I set r equal to sine, or what if I r equal to cosine, r equals to tangent, r equals to secant. Just try things over and over and over again until you find something that works. If you do that while you're teaching, you waste a lot of time during class, but I usually do actually pretty well on math exams just because I try stuff, you know. I don't give up immediately when I don't remember something. I just try stuff until it works. Okay. Any questions about question 1? Does it all make sense? Okay. Now, question 2 says, we want to evaluate the following integral over the surface S and the vector field F. In your solution, please make use of the divergence theorem. So, the divergence theorem says if I want to take a double integral, or a surface integral over some vector field. Surface integral over some vector field. And the surface we're talking about is not just any surface, but the surface is particularly a boundary of a 3D region, where that 3D region is it's such that the boundary is at least piecewise smooth. So you don't have a fractal boundary, but it's a normal looking boundary of a 3D region. And then we said, according to the divergence theorem, that is the same thing as taking a triple integral over the entire 3D region of the divergence of F. We can write dv because we're talking about differential chunk of volume. Oh, I actually gave you that formula right here. I didn't even need to rewrite it. Okay. So there it is. And, of course, this surface, we talked about how this surface is just the upper half of a sphere. Okay? And so we don't actually have a case where the surface is the whole boundary of a region, right? The surface that we're dealing with is just the top of the sphere. So let's talk about a region R that is the top half of a ball, centered at the origin and has radius A, okay? So this is not just the top half of the sphere, but I'm talking about the three-dimensional solid that makes up the top half of the ball. Then the boundary of R would be both the surface that we're talking about here, this capital S surface, and it would also have to include the disk in the xy plane that would make up the bottom of the boundary of the top half of the ball. So the boundary of this region R is not just the surface S, not just the top half of the sphere, but it's also the disk. Yeah, I include both of those together. Okay, let's first think about the integrand here. So the integrand says that we're taking the divergence of F. And the divergence of F means you take the dot product between nabla and F, which is going to be, oops, this is not a vector. A dot product is always a scalar. And so this is going to be the partial with respect to x of x plus the partial with respect to y of y plus the partial with respect to z of negative 2z. So what is my divergence? 0. Yeah, it's 1 plus 1 plus negative 2, which is 0, okay? So the integrand here of my triple integral is 0. We're talking about taking the triple integral over the region R of 0 and that is 0. But the divergence theorem tells me that this has to be equal to the surface integral over S of my vector field plus, don't forget, the surface integral over the disk in the xy plane of my vector field. Okay? So these two surface integrals added together have to equal 0, again, according to my divergence theorem. So the next thing we need to do is we need to show that this double integral is equal to 0. And if this double integral is equal to 0, then 0 is equal to a surface integral plus 0. And so that means this surface integral would also have to be 0. If only we can show that the surface integral over the disk of my vector field is 0. So let's do that. To take the integral over the disk, we may not even have to do any work. If we think about this for a moment. If you look at my vector field capital F, right, this is defining a three-dimensional vector for every point in space. And this vector has a vertical component of negative 2z. So how much it points up or down is going to be negative 2 times its z coordinate. So the surface we're talking about right now, the disk that lies in the xy plane, the z coordinate at any point in that surface is 0. Yeah, everywhere in the xy plane, the z coordinate is 0. And so anywhere that's in my disk, in the surface that we're talking about right now, the z coordinate so it should be 0. So negative 2 times 0 is 0, and that means the vertical component of any vector in this vector field in the xy plane, the vertical component has to be 0, okay? So if you think about that, here's my disk lying in the xy plane right here. The flux across that disk is just going to be adding up all of the vectors that are orthogonal, or not orthogonal necessarily, but have an orthogonal component, right? Something that pokes through the disk one way or the other. And since all of the vectors are lying flat on the xy plane, and the disk itself is lying flat, there's actually no flux through the disk, right? All the vectors are sort of tangent to the disk. There's no vector components that move through the disk. If you think about the vector field as being like a fluid flow and describing the direction and the speed of fluid flowing, then there's no fluid flowing through the disk. There's only fluid flowing across the disk. And so in terms of this surface integral, it's going to be 0 just on the basis of just on the basis of saying, if I took a dot product, right, between the vector field and the normal vector of the surface, right? If you found a normal vector to the disk, then of course it would be pointing vertically up or down because the disk is flat. And then, again, you take the dot product. The dot product is 0 if the vectors are orthogonal. Yeah, and so since the whole vector field is tangent to the disk, the normal vector would be orthogonal to the disk, and their dot product is going to be 0. I don't know if I'm making any sense. But what I'm trying to do is I'm really trying to convince you that this surface integral over the disk has to be 0, just based on what we know and the way that we interpret these surface integrals. And so if that is 0, in the sum of that surface integral with the surface integral that we're actually trying to compute, remember our goal here was to compute the surface integral over S, that plus that is 0, 0 plus this is 0, then the surface integral we're trying to find is 0. So here in question 2, I hope that I hope what I'm saying makes sense. But if you happen to know about the divergence theorem and you tried to apply it, and you happen to really think about sort of the geometry of the situation, and you can reason to yourself, and you could even carry out this whole calculation and it wouldn't be that hard, you could save a whole lot of time. You could save a whole lot of time and stress, because this was kind of difficult. I mean, no part of it was hard, but it took a long time. It took comparatively longer. Okay, so question 3. It says we want to evaluate the following surface integral over the vector field f. In your solution, please make use of Stokes' theorem. So, here's how we do this if we want to use Stokes' theorem. We say, okay, Stokes' theorem, and I gave it to you. Here's Stokes' theorem. It says we have a vector field G, and since I'm trying to find the surface integral over my vector field f, what I want to do is I want to find a vector field G such that the curl of G is equal to f, and then if I can find such a vector field, then evaluating the surface integral over f is going to be the same thing as evaluating a path integral around the boundary of that surface of my vector field G that we found. Okay, so step number 1 is to find G such that curl of G is equal to f. And we said the other day, we said this can only be done This can only be done if what? It's only possible to find a vector field G such that the curl of that vector field is equal to f if the divergence of f is 0, right? Because if the divergence of f is 0, that would mean the divergence of the curl of G is 0. And we said that that was true for every vector field with continuous second partial derivatives. Okay? And so this vector field f, it has continuous partial derivatives. And so the vector field G must have continuous second partial derivatives, so this has to be true. And so we can only find this kind of vector field if the divergence of f is 0. We just showed on the previous page that the divergence of f was 0, and so we're actually good to continue here. So we're trying to find a vector field G such that the curl of G is equal to x, y, negative 2z. Oops. And of course, the curl of G is going to be the partial of G3 with respect to y minus the partial of G2 with respect to z. The second entry is going to be the partial of G1 with respect to z minus the partial of G3 with respect to x. And then the partial of G2 with respect to x minus the partial of G1 with respect to y. So, G, this vector field, we've got to try out some things. We've got to guess and check. Let's make the partial of G3 with respect to y, let's make that partial derivative equal to x. So that means if I look at the third entry of this g vector, and I take the partial with respect to y, it has to give me an x. And so that means the third entry of this g vector has to be xy. Very good. That all means if I want this to be just x, that means the partial of g2 with respect to z, that has to be 0, so that I don't pick up anything extra there. But that's fine. We'll make sure that works in the end. For the second entry, I want this to be a y, so let's make the partial of the first entry of g with respect to z equal to y. So let's make that yz. Okay. But this says actually not just the partial of g1 with respect to z, but it says the partial of g1 with respect to z minus the partial of g3 with respect to x. Ooh, but the partial of g3 with respect to x is y. So I'm already subtracting a y. So if I want this to be a y, blank minus y equals y, this really needs to be 2y. And so maybe the partial derivative of the first entry with respect to z should be 2y. And so I'll need to make the first entry 2yz in order to get this y in my second entry. Okay, and then looking at the third entry, partial derivative of g2 with respect to x. We haven't figured out what that's going to be yet. Minus the partial derivative of g1 with respect to y. So the partial of g1 with respect to y is going to be 2z. So this is a negative 2z. Oh, and that works out because we wanted a negative 2z. All right. So let's make the second entry a 0. And if I were taking this exam, I would like really closely double check all of these again just to make sure it works exactly how it's supposed to. But I think we found a vector field G that if you take the curl of G now, then the curl of G is our vector field F. So now we can say the surface integral over F is equal to the surface integral of the curl of G. And Stokes' theorem says that all of this should be equal to the path integral around the boundary of G. No, sorry, the boundary of S. That's an S. The boundary of my surface of G. Okay, so the way we do a path integral, is we choose some parameterization t of the path around my surface. My surface is the same that it always has been. It is the upper half sphere with radius a. And so what is the boundary of my surface? Let's graph it. I'm asking about what is the boundary of the upper half sphere? We'll say A is 3 for the sake of GeoGebra. All right, this is the upper half sphere. What do I mean by the boundary of this surface?
Half a sphere.
So the boundary, the edge of the top half sphere, is going to be the edge that lies on the circle in the xy plane. There's a circle in the xy plane with radius a, and that's the edge of this surface. Does that make sense? Like the surface just ends abruptly in the xy plane. So that circle is what I mean by the boundary. Okay. So that means the boundary of S is going to be some parametric curve, and I'm going to parameterize this by saying A cosine t and then A sine t. That's how you parameterize a circle in the plane with the radius A.
Is one dimension lower than the
Yeah. Yep, and t is going to go from 0 to 2 pi because I'm trying to trace the whole circle. And then what goes in the integrand is going to be the dot product between my vector field and the derivative of the parametric curve. Not the parametric curve itself, but just the derivative. And so my g vector field is 2yz, 0, xy. The derivative of my curve is going to be negative a sine t, a cosine t, 0. Okay, now look at the dot product. In the dot product, 0 times a cosine t is 0, xy times 0 is 0. And so what I'm left with, the only thing that remains in my integrand is going to be 2yz times negative a sine t.
0.
And sine of 0 is 0. Sine of 2 pi is 0. And so the whole thing has to be 0.
Z is equal to 0.
And yeah, since we've got 2yz and the z in my parametric curve is 0, we set z equal to 0 when we replace that, yeah. There's multiple reasons why that's 0. Yeah, so then question number 4 just says, in the first 3 questions, you solved the same exact surface integral over the same surface in the same vector field. You should have the same answer to all 3 questions. And the answer is yeah. So that's good. Math should be consistent. We should have the case where whether we use the formula for actually evaluating the entire surface integral, the formulaic way, or we use the divergence theorem and we think carefully about the geometry and the consequences of the divergence theorem, and we of course have to think about the disk because we're thinking about the boundary of a whole 3D region. We got 0, and then of course if we use Stokes' theorem and we found the curl or the anti-curl, find the anti-curl of the vector field f, and then we took the path integral around that boundary, we also should get the same thing. Okay.